Newton's third law in rocket science. So we have learned Newton's first two laws, and you're going to answer a question. You're going to state what they are here in the embedded video questions. Newton's third law of motion is the new one that we're going to learn. So it is that for every action force, there is an equal and opposite reaction force. So let's look how some examples of that. So you will have something like a car driving into a brick wall. So there's quite a big force of the car exerting that force onto the wall. But it's not just the wall that experiences that force. The car is going to experience that force because the wall is going to push back against the car. And that's what's going to cause the car to crumple, right? And so it's an equal force in the opposite direction that the car is exerting the force. You might see it in a cannon launcher. So this kind of light gray outline here is the cannon launcher where it was when it first shot a cannonball out. And so, of course, the cannonball is going a force in that direction, the action force. The reaction force is going to cause this cannonball launcher to move in the opposite direction. So kind of like a kickback. And that is why the new outline of the cannon is a little bit farther back, right? It got pushed back when it expelled the cannon. Any stationary object is exerting a force on, say, a table or the ground on Earth, and that Earth is pushing back on that book. That's why that book doesn't fall to the center of the Earth. When we walk or run, we are pushing against the ground in this direction here, and the force of the foot, force on the foot from the ground is equal and opposite, so that propels our body forward. If two people are on skateboards and they push against each other, they will experience, if they're not on skateboards, they'll experience a reaction force, but they might not move. But if they're on skateboards, because of the low friction, they're going to move away from each other. If they push on with each other's hands, they'll actually move away from each other because of that equal and opposite force. A soccer ball hitting Earth will experience an equal and opposite reaction or force, reactionary force, which will make the soccer ball go flying in the other direction. If we kick a soccer ball, the soccer ball will also push back against our feet. The harder we kick the soccer ball, the greater the force, the more we're going to feel that on our feet, right? So if we are, say, barefoot and we kick a ball really hard, that's going to hurt because there's going to be quite a bit of force exerted by the ball in the opposite direction. So one question we're going to look at is, why is it that if, say, I kick a soccer ball and it goes flying this way, if it's an equal and opposite force that the soccer ball is exerting on me, why don't I go flying at the same acceleration in the opposite direction? We're going to look at that mathematically. So here's the problem we're going to do. According to Newton's third law, when you kick a soccer ball, the ball exerts an equal and opposite force on your foot. So why does the ball accelerate more than your foot does in the opposite direction? So we're going to do a little math. Newton's second law states that force equals mass times acceleration. We're going to solve for acceleration. We're going to get a by itself. So we're going to divide both sides by a. Oh, I'm sorry. We're going to divide both sides by m. We'll get a by itself, and so we'll have the acceleration equals the force divided by the mass. So the acceleration of the ball is going to be that force that we kick it at, 300 newtons, right? That's right here, divided by the mass of the ball, 5 kilograms. So that's going to give us an acceleration of 60 meters per second squared. Now you're going to calculate the acceleration of the foot, or of the whole person, in the opposite direction. So we're going to use that same formula, but now we have to use slightly different numbers. They're experiencing the same force, 300 newtons, equal and opposite force, but now that force is acting on the mass of the entire person. So you're going to do the math here. What are you dividing by? Equals what number? So you'll answer that in the video here. And you'll see that it's a much smaller number. So while the force is equal, and the ball and your foot are experiencing equal force, the force is acting on a much bigger mass here. So it makes your foot accelerate in the opposite direction quite a bit less. And since your foot was already moving forward, that negative acceleration is it's still probably going to move forward a little as you kick the ball, but it's going to move forward at a slower rate. It's going to decelerate. Okay. You will watch this video and answer a few questions after these notes videos. Let's look at rockets. So in class we are building these paper rockets. How an actual rocket works is it shoots, it has a big combustion burning of rocket fuel in here, which shoots exhaust out of the back, and it'll be sort of like a big flaming hot gases, right? So it'll have that big fiery looking rocket exhaust. And that is, of course, going in this direction. And it's going to exert an equal and opposite force in that direction, and that is the force that moves the rocket in the opposite direction as the gas is escaping. You have maybe experienced this when you blow up a balloon and you don't tie it, and then you let it go, and all the air escapes really fast out of the balloon, and that makes the balloon move crazy all around the room, right? So opposite force making it move as the gas is escaping this way and pushing against the air in the room. That the air that's in the room is going to push back, going to propel that balloon forward. Now, the rockets we're building, the paper rockets, we're not shooting hot gas out the back of the rockets. It works a little differently. We're pumping air into our rocket launcher, and then we're pressing a button, and it's going to release the air all at once from the launcher so the launcher has a PVC pipe that goes inside of the tube of our paper rocket, and we're pumping air into that and then releasing it all at once, and it's pushing against the top of our rocket here and sending it up into the sky. Lots of fun. So that's an example of Newton's first law of motion, that an object at rest remains at rest unless acted upon by an unequal force. So that paper rocket will just sit on the launcher until we pump air and release that air, shooting it forwards. Okay, that is it for... Oh wait, there's one thing here you're going to answer in the video. You're going to take one of these situations and you're going to explain how it demonstrates Newton's third law of action, or you can use a different situation of your own creation or idea to explain Newton's third law of motion.